Okay, so the screen recording still don't have any um, videos for the class, unfortunately, but I'm still working on it. Okay, so for the activity today, I'd like you to write a for loop in C, if you remember how to do that, and then try to write the equivalent in assembly language. And then if you have time, we'll probably go till 8:15. Write an if-then statement in C and see if you can find the equivalent in assembly language and how long each of them might take. So. Yeah, it's up to you.
Where's the homework?
Oh, over there. Yeah, this would be for the pick, so you'd have to write the printf. But if you just want, so why do you need a printf?
We're just trying to get a.
Oh, okay, that's fine.
Yeah, we're not. I'm also using print.
Oh, you just want to do something.
Yeah.
Okay.
There you go. I like it. See the decks? Correct. Alright. Now the next one is all this. So that, then do, oh, yeah. Yeah. This is cool. Yeah. To, right? You can be that guy. You can do whatever you want. Okay. And then we're gonna put mini reg to. You can move it to another register if you want. You don't have to use decker. So decker W reg is already. So loop. Why do you do not? Okay, good. And then loop. Loop one. Colon. One. So he's trying to be that will say.
So, you got anything you want to share yet?
No, I don't think I can write the equivalent assembly language printf, so I'm probably going to remove the rest.
Yeah, don't worry about the printf or even what's inside the loop. So
Can't exactly remember
for the loop, you just got decrement and branch. That's not zero. Yeah, that's exactly what it is. Then you would just move however many times into W2. Yeah, that's exactly what it is.
Alright, I don't know if you have the C right. I can't remember, I don't take the C before.
Well, the thing with the for loop is you can just set it to, so you got what you want to set it to, and then you got the ending term here, and then you got decrement here, so you got it all in there.
Alright, thanks man. I'm gonna work on the if else.
Okay.
Well, actually I got the C already,
So for the if else,
Yep.
you might want this instruction.
There was one,
CP.
it was called
It's CP, and then you have one register, and then you have branch after it, maybe.
CP.
That's a compare instruction.
Okay,
So you could compare, I think you can compare two registers, or you can compare a register to a literal.
alright, I'm just gonna look for it in the manual real quick and put it right here.
So if the registers are equal, then
There we go.
You can have a branch with a bunch of different conditions. I think you can even have greater than, or less than, or equal. I think pretty much anything that is in the if in C. How's it going over here? Yeah, you could do a bit test, get back that, and you could check the status
so you have a branch not zero, and then a branch zero. Would that work?
Yeah, you could have a branch not zero to somewhere, and if it is zero, it would skip that and go to the next thing. So that would be like the else.
Okay. But what if it's three conditions? So you have three branches.
Three conditions. So if something's not true, else if that type of thing. So you could have like compare this to this, and then branch to the true thing, and then if that's not true, then another compare here. So that would be like if else.
So another compare. Okay.
Yeah, another compare, and then if none of those are true, then the bottom thing.
Yeah, because I was really worried about having two branches, but then the second branch is not acting on the first.
Yeah, and then so you'd have all your statements, and then you'd want to make sure that you have a branch like default or false, just to make sure that you don't accidentally go to the false thing. This is just one way to do it. There might be a clever way to do it with the bit test instructions as well. Okay. Yeah. Okay, great. No, no problem.
How might they change?
Hmm? How long?
Okay, how long?
Yeah.
Oh, that takes a lot of hundreds. It could be true. We found something about it. Yeah.
Okay. What do y'all got? Okay. So the for loop is you set up something and you have the end condition here. Great.
Yeah.
And then if else you're doing branch not zero. So you're doing bit test, skip if clear. Okay. Okay. So you need a compare instruction. Okay. So it compares two things and then sets all the appropriate bits in the status register.
Yeah.
There is a CP0 which only takes one argument as well, so you can check if something is equal to 0, greater than 0, less than 0. I don't think it's faster, but it might look a little cleaner. Yeah. I've seen a lot of the disassemblies seem to use CP0 exclusively, so maybe it's faster or just easier to compile to. Okay, great.
Yeah.
Yeah, it looks great. That might work. I'm not sure if the and sets the arithmetic status register. It might set the 0. But so would this be for the for loop or for the if statement? You might want to use this CP instead. I'm not sure if the and instruction sets the status register. Yep. That looks good. Awesome. Looks good. Cool. Thanks. Okay. Anybody got any questions about this? Otherwise, I think we'll wrap the activity up. Oh yeah.
So assuming these are the exact same, it would just take.
Yeah, it should be pretty easy to compile these statements unless the variables used are larger than 16 bits. And then, depending on the compiler, you may, if you're doing it in assembly, you may know which section of the longer variable you might need. So you could do maybe a little faster, but these should be pretty easy to compile. All right. If there's no questions, I think we'll kind of keep going then. Okay, so today I wanted to talk more about the stack a little bit. I wanted to introduce interrupts, which are kind of a way of writing programs. And I wanted to talk about the last few instructions that we're going to kind of cover in the class, which is the compare and branch, multiply and divide. And then if we have time, I want to talk about timing for C functions, how long it takes to call a C function and how much extra time it might take. And then maybe some buffers in C. Because next week we're going to kind of start talking about some of the peripherals. I think we might start with the UART and timers, and then talk about interrupts and kind of keep going with the class. But before I start, I just wanted to say if anyone needs more time in the homework, please send me an email. So just so I remember basically. And if you need more time, that's fine. But basically, I want to get the homeworks to the TA pretty early next week, so he has enough time to grade them and get them back to you. And then I'm going to assign the second homework later today. So yeah, just try your best. And the first homework, I don't think we're going to be too harsh grading. So if you just turn in your best shot, that's fine, and we'll keep moving with the homeworks. What else? And I apologize, I haven't been able to record the lectures yet, just because I'm trying to record them with my laptop, and I don't have a lot of hard disk space left. But maybe what I'll do is I'll post reading for each of the lectures that we've covered, just kind of the source material that I've used for the lectures. That way you won't have to dig through all of the guides and data sheet. You can just look at the specific sections that I used for each lecture. So hopefully that will be helpful. And then I uploaded all the in-class quizzes as a Moodle quiz, if you've seen that yet. And I'm trying to really put a lot more quiz questions on there, just for like test prep and just general kind of check your knowledge type stuff. So yeah, any questions about that? Yeah. Okay. Yeah, maybe I'll try to do that. Yeah, that's what I'm trying today, is just streaming directly to my cloud drive. But I think there are upload limits to most cloud storage. And the other thing is the videos are going to be like 2 gigabytes, and so a lot of cloud storage has limits for how much you can upload at once, and it's tough because in order to actually see the board, you need like a pretty good video quality, and a lot of basically a way of making the file size smaller is more compression, but then you can't see anything, so it's kind of pointless. But I'm sure I'll figure something out. In the meantime, is reading okay, like uploading reading material? I know it kind of sucks, but it's nice to have videos. But yeah, this class doesn't have nice recording stuff built in, unfortunately. So yeah. Any comments or questions? Okay. So last time we talked about the stack a little bit, and there was a big problem. And that's, I said that W14 was the stack pointer. It's actually the frame pointer. And W15 is the stack pointer. So, I don't know. It matters for the frame pointer. And it probably matters for the stack pointer too, but if you're using the stack instructions, then push and pop, then it happens automatically. So I wanted to just keep talking about the stack a little bit. And the reason that I keep talking about the stack is it's really important for C, okay? That's why the stack is important, is for programming in C. Because when you're looking at disassembly files, if something goes wrong and you're not sure what's going on, then it's helpful to have knowledge of the stack, what's on the stack, and what the stack is, what the pointers are, what the overflow registers are. So this is really a C concept. If you're writing an assembly language program, then you can make your own stack. You can make the stack whatever you need it to be. It's still, as a programming concept, is still kind of handy because it's like you've got this thing that you know how it works and you know what's going to be saved to it. But it's really important for C, and it's also different from the stack and other concepts. So stack. So the stack is this thing that is basically a section of data memory that you have stored, and you have a pointer to it, and so it's just like this little subsection of data memory that you're using to store variables. And other concepts, has anyone ever done like app development or web development? So in other kind of programming paradigms, they say the stack is basically knowing your platform all the way from like your website to the networking protocols to the hardware. So they call that the stack. It's like this paradigm that starts with like user interface, and then it goes to software, and it goes to like the networking layer, and then it goes to hardware. So they call that the stack. So it's very different. So just thought I'd share that because it might be kind of confusing. But for programming embedded systems, the stack is where you store your variables when you're doing function calls. And so this is in the programmer's guide. They have a little section on frame pointer usage in section 4. And again, I'll try to post all the source material for the lectures in a easy to kind of look up form. But basically, so they have a call statement to a subroutine, and they're starting in another subroutine. So they have task A, they call it, and then they have compute. And so they're in task A, and they want to call compute. And they use call here instead of rcall for some reason. And then at the end of compute, they have a return. So in this case, they're putting parameters on the stack to the function. So they want to save W0, W1, and W2. So before you call the function, because after you call the function, you can't save them. So before they call the function, they push them on the stack. But does anyone know what you have to do to initialize the stack in your assembly language program? Yeah, it's an assembly language directive. And let's see if I can find it. So you do stack space 32, and then it's basically just an address location, and then you move the pointer to the stack to register 15, W15, which is the stack pointer. So that happens before all this stuff, basically. Oops. So that happens before all this stuff, and then any parameters you want to save, you push them on the stack. And so what does that do? So if you push W0, W1, and W2 on the stack, what that does is it puts W0 here, and then it increments the stack pointer to here, and then puts W1 there, and then it increments the stack pointer to the next memory location, puts W2 there, and then increments once more to the final location. And then when you do a function call, what happens is it pushes the program counter onto the stack, which is a 24-bit or 32. It takes up 2 word locations in memory. So it puts the lower 16 bits first, and then it puts the upper 16 bits second, 2 memory locations, and then it goes to the next slot. Why does it do this? Yeah. Yeah, exactly. Because the only way it knows where you are in program space is via the program counter. And so you have to save that actually in data memory to get back to it when you're using call and return statements. So it's a way of basically referencing where you want to get back to. So in this diagram, it also shows a frame pointer, or a frame basically above the top of the stack initially, and it shows W14 somewhere in here. So this is W15 stack pointer. Where exactly do you think W14 would be up in there, the frame pointer? Is there any way of knowing, really? Is there some place it would be? There really isn't, because it just depends on whatever subroutine you're in and whatever it's doing. That's like the local variable space. So this is just kind of like the space where you're storing local variables in a C function. So it could be pretty much anywhere, but you do need to know kind of where it is. And so when you call a compute function, sometimes, well, you really should call something called link, and then allocate the number you need. So this is basically the number of like register locations that you want for your local variable space. And then you want to free them up at the end, which is ulk. So these are instructions. And what these instructions do is they save the frame location that you were at before. So if you're in one function and you call another function, you save each frame location that you were in before. That way, if you call a function from another function, you don't lose those local variables. Does that make sense? So as an example, maybe I'll write it here. So you have main function, void, main, void, and you have the int a, right? So this could be on the frame, and you want to call func1 with a as a parameter, and then you want to do a plus equals 1. So if func1 takes that argument and then changes it, you don't want a, say you initialize a to 0, and you're doing other things with a down here. You don't want the function to change a, right? Because that's in your variable space. You want to be able to write a program, call a function, and not have it change your local variables. And so whatever local variables you have that you're using in data memory, you want those to not be overwritten. But you also need to know where they are when you call the function. And so, like when you're referencing a, say this points to the lower part of a, or say a is just a 16-bit thing. So if this is pointing to a, for example, and then you do something where you want it to still point to a when you come back, you have to then save W14 in the stack when you call a new function. So then when you do the link command, what the link command does is it says how many locations your new frame is, and then it saves frame pointer where you were at before. So it would save, I guess it would save, how should I write this? Frame pointer from task A. That's W14. So it saves where W14 was before. However much space you need there. It just depends on, it just saves the frame pointer. So it would just be one word location. And then it increments the stack pointer again. And then it points the frame pointer at, okay, so we were right here, we saved the frame pointer from before, and then we point the frame pointer at the next available location. And then the stack pointer then, so if we link 4 locations, the stack pointer then would be 1, 2, 3, 4 away. So then this is where the new stack pointer would be. When I first saw this, I was really confused. And it's different really for every microcontroller architecture. But to me, it kind of makes sense. The basic things that make sense to me are you need to save the program counter. So you need to save the program counter so you know we're going to return back to it. So that's kind of the basic thing that you need to do. The other thing you need to do, to me, which makes the most sense, is you need to save the local variables from where you were before. And so in this terminology, they call it the frame pointer. You have to save the frame pointer on the stack. And then the other stuff, it seems kind of arbitrary to me, but it does make sense when you want to push something on the stack. You save it and then you increment, and then save and then increment, and then you do the call and then save that. And then the stack pointer is way down here. So it's like, how does it get back to when you want to do push and pop, you want the stack pointer to be at the same location as before. So how does it get back here when you want to do a pop instruction? It depends on the unlink and return statements to get back to the right location. So we're down here, our frame pointer is in the right spot to do whatever we need to do in the compute instruction. Our stack pointer is in the right spot. Here is going further down is just the rest of the stack space to do whatever we need to do. The stack could be composed of like tens of these, depending on how many functions you have. You might have tens of these like little sections where you're storing stuff and saving stuff, and you're off in one function to the next function to the next function, but everything's all in a row. But to me, this is kind of a delicate concept because to me it's kind of complicated starting off, and it seems like lots of things can go wrong. So each function has all this space. I could see it being difficult to know how much space to allocate on the stack when you're starting out, to know basically how much you want to allocate. And if you guess wrong, then what are the penalties? So you have like memory location further down that might get overwritten that you need for other things. So I guess to some people this might be second nature, but to me it kind of seems complicated and maybe prone to error. But I think using this a lot, and C compilers in general are pretty good at figuring out how much space each function will need, and figuring out how much stack space to use. Okay, so questions about this? Yeah. Mm-hmm.
Could we like do that? Say we want to do something, we push both of them on the stack and pop them in reverse order.
Yeah, you could. So what pop does is you're not able to say what order. Does that make sense?
Yeah.
So when you unlink and then return, the stack pointer will be right here. What you could do is reference W15 directly, and then put W15 here, and then put that into W2, because the two variables are saved separately. They could put that back into there, and then go back here and put that into your other register. But if you just do pop, then pop takes one argument as an instruction, and that's where you want to send it to. Yeah, so you're right. So you could do pop. You could do pop in reverse order. Yeah. Well, the push and pop commands are kind of handy, and when you use them, then other people reading your code probably know what you're doing. But if your assembly language isn't that complicated, then maybe it's not necessary. I'm not an experienced enough assembly programmer to really answer that question adequately, but that's kind of my thinking. And a lot of assembly programmers, yeah, the time I did spend kind of in a development environment, the programming manager wanted to keep things as simple as possible. he only allowed if-then statements and for loops in C. Nothing else. No switch, no while loops even. And so he wanted, his code was just basically a ton of nested like if-then statements and then maybe a couple for loops. And so that just, he was able to just go line by line and know exactly what was going on. And the same was true for the assembly. When we had to do assembly for something, it was always very organized, and each function kind of did exactly the same thing. So whatever works for you, I would say, or the team that you're working in. Okay. So then we do our function, we do our compute function, then we're doing all the stuff that we need to do, and then we need to get back. So the first step, what's the first step to do when we come back from the function, when we're coming back from the compute function? I'm going to call these, I'm going to call this like task A, and I call this compute. Here's another question before you answer that one. So we're supposedly passing W0, 1, and 2 as parameters. What does that mean? So they're on the stack, right? How are they used as parameters, do you think? So it says push parameter 1, push parameter 2, push parameter 3. Why are we doing that? Any thoughts? Just in case they get used, overwritten or something, we want to save them. It's like just for fun. So if we're passing W0, 1, and 2 as parameters, then they're going to get used and overwritten in the function. That's the idea. That's why we're pushing them on the stack. So W0, 1, and 2, they're not even referenced in C. They're kind of underneath the surface. So when you pass parameters, you kind of use these working registers just generally. So I think in general, W0, 1, 2, and 3 kind of get used a lot. It's up to the assembly language programmer to decide how you're going to pass, which registers you're going to pass to various subroutines and functions. The compiler seems to use W0, 1, and 2 a lot, and so you push those on the stack because they're actually passed. They're not really passed to the subroutine. They're just there. So you're storing things in them, and then when you call the subroutine, you have to know that they're there. But in order to save them for use when you come back, you push them on the stack. And so what if you want to return a value? What would you do then? If the subroutine needed to return a value. So which frame would you put it on? So you would maybe put it on the local frame somewhere, but you're not, your frame pointer doesn't go to the local frame until after the unlink step. So you could put it on the local frame before the return. Yeah, that's a good point. But then your local frame, when you do the unlink, it points to variable A, which is your local variable. So you might not want to overwrite that. So one thing that you could do is you could say, all right, I have these values as working registers that I'm passing. I'm just gonna not pop them back, or I'm gonna save the return value of the function into 3 other working registers or something. So you could just decrement the stack pointer to overwrite them. Or you could save the return variables in other registers, other working registers. Any other ideas of what you might want to do with return variables? So if you had a return variable, return value, and maybe you had a local variable b that you're putting it into, then after you do the unlink step, it would maybe, you could set it up so that it points to b. So after you do unlink, the frame pointer is pointing to b. And then you could move the return value into the frame pointer. So that's another way that you could save return things, and then keep your stack nice, push and pop everything. So I think that's probably a nice way to do it for C programming, because when you return stuff, you always put it in a return variable. So after you do unlink, you might have a move statement. So you might move whatever local variable, maybe w0, into the value at w14, and then do a return. You might do w14 minus minus. But yeah, it's kind of complicated, and there's no real right way to do it. It just depends on which subroutine you're calling and what the assembly language programmer wants to write. And that's another reason why assembly, you can do things a lot faster, but it just depends on so many other factors. There's so much extra complexity that any sort of speed advantage, I think, is outweighed by complexity advantage when you're writing a massive application in assembly. There's some people that would probably disagree with me, but I think everyone would agree that there's just more complexity involved. But the reason we're kind of going over this is so if you're writing a C program and things are going wrong, so you can look at the disassembly and have some idea of what's happening. That's the reason we're going over this. Okay, so you might want to move after you do unlink, so you're in the function, you're in compute, you're doing some stuff, maybe compute returns an int. It might take an int as an argument. You're doing some stuff, and then you return So after you do unlink, W14 will go up here. And I believe after you do unlink, the stack pointer then will point here. Actually, unlink I'm not exactly sure how I think actually what happens is you do unlink, you have the stack pointer here, the frame pointer was here. So the unlink command, the stack pointer then will point at the frame pointer. And then it will load the value of the frame pointer into W14. unlink command, the link command saves, is this shown? Okay, so pop-up stack is at the top of however many local variables. And the link command moves the number of variables in, and so the unlink command needs to know how many spaces below the frame pointer it is. So when you do the unlink command, W15 goes to the former frame pointer. It loads that into W14. W14 might be anywhere because this was after the function. It could be anywhere in here. But whatever it is, you load the former frame pointer into W14. In this memory location is an address. And that address is where the frame pointer was before. So when you load that into W14, it then points to the frame where it was before. And then after the unlink command is done, I think W15 is still here. And then you might save whatever return values you have into the other frame. And then you call a return statement, and W15 loads the two words into the program counter. So now the program counter is pointing back to the original function. So the program counter goes back here. After you do the return, then the program counter goes here. So it loads those values into the program counter, there, and then it points here. And you're ready to do the pop statement. So then you would do pop W2, pop W1, pop W0 in reverse order. And then you might want to move W14 somewhere. Maybe even decrement W14. So then it's pointing to variable A. You might want to move W14 into W3 or basically just some working register. So that's what happens when you call a function, maybe. It depends on the compiler, or if it's an assembly language programmer, it depends on you. But this is used often enough in compilers that it's helpful to go over. Okay. Questions about this process? So the idea with this class is you may not use this stuff when you program microcontrollers in the future. You may never use it again, which is kind of sad. It's sad that you might not use it again, but maybe even more sad that you have to sit here and listen to it. There's a couple schools of thought. One of them is you should see how things work at least once in a class setting, and it will be helpful down the road if things go wrong or if you're just curious. The other school of thought is it's a waste of time to go into more detail than you have to. And so sometimes this course is taught more from the latter perspective, and they do more like building robots. They might do a little bit of this in the first week, and then build robots and do projects the rest of the time. And then when you run across things that go wrong and you want to look into this more, then you do it at that time. So I don't know which one is better. I kind of tend towards the latter, but when I took the course, it was more assembly and computer architecture oriented, and I really enjoyed it, and it made understanding things easier later on. So that's why we're going over all this stuff, basically. All right, let's do a 10-minute break. How about? Come back around 9:10.
Alright, I understand that. Sorry, I mean, this thing is just really.
Oh yeah, for sure.
So I understand that I push those and they go in the stack. I understand I need to. Okay, so that keeps just changing the pointer. So I just call W2 back, call W1 back, call W0 back. Is that right? Or
Yeah, so call compute does all the stuff, and then when it comes back, you hope that the stack pointer points to the right location. It has to.
alright, so
So if you do something in this function where you're changing W15, that could cause problems. Because when you come back, W15 could point to a different spot. And you wouldn't be able to pop anymore. So yeah, there's nothing preventing you in assembly language from making catastrophic errors. Unfortunately. If you write in C, then this kind of stuff is taken care of for you, and you can make other errors. Yeah.
This might be stupid, but give me a second. I was doing the homework. If bear with me, my screen has a really high resolution and these programs aren't designed like this isn't scale to it.
Yeah.
So that's really fun. So when I was implementing the
That's fine.
swap, sorry,
Mm-hmm. Right here.
yes, I don't know why. Okay, so one thing I was really confused about. So once I save these variables, when I implemented it like this, when I looked at, so originally I had W0 as, what did I have it as? I set it to 15, and then I set, or sorry, W0 was 6.
Mm-hmm.
Wait. Variable A was 15 and variable B was 6,
Mm-hmm.
right? And now when I come up here to call the swap, I want to store them to registers. And so I use the hashtag to store the value. But it turns out hashtag stores the address. Doesn't it store the value? Or does it? I was confused about that because usually when you want to use a literal, you use hashtag 0x whatever, which stores the value. So
Yeah. No hashtag would
be the value.
be the value.
Okay.
Hashtag would be the address.
Okay. I thought the address was brackets.
Okay, so brackets is like asterisk pointer in C, and you use that for working registers. So here you're moving the address of variable A to W0, address of variable B and W2. You'd want to do XOR and use all brackets. I think you can use all brackets in all these operations so that it's moving the pointer locations.
I see.
The way you set it up here, though.
When I took out the hashtags, it worked. So
Yeah.
that was just really confusing to me. I was
Oh yeah,
debugging for
because
30
it's
minutes.
literals as
Yeah.
well as then dereferencing an address.
Yeah.
They use an ampersand. I mean, I don't know why they didn't just use the C pointer notation. But
Yeah. Okay. Cool. Just making sure I wasn't losing my mind.
no, yeah, this assembly is not great. This assembler is not awesome.
Yeah, the other thing I don't like about it is, I don't know, when I first learned programming, I started way at the top with MATLAB, and so when I had an error, I could Google search and I'd find tons of documentation.
Yeah, not for this.
Yeah. When I started to Google search stuff for this, I find Intel x86 assembly.
Right.
It looks completely different. I shouldn't say it looks completely different, but there's different nuances that don't apply here.
Yeah, it's a complex instruction set, so it is a different world.
The other weird error I got, I don't know if you know anything about it, but when I declared variable A and variable B, when I had it as 1 byte, I got this weird compiling error that said something about you can't like operate on an odd address or something.
Yeah, that is true because, so is this specified in bytes then?
Yeah.
I thought it was words. Okay, that's fine. So it's in bytes, so the minimum is 2.
Really?
Yeah, because there's instruction operations that can operate on bytes, but the addressing will only point to words. So if you have something that's 1 and it doesn't sit on an even address, it sits on the odd address, then you'll get an error. Because it's designed to be accessed 16 bits at a time.
Yeah. It's interesting because when I googled the error, apparently if you declare it as a 2-byte variable and then declare it right away, like change it to a 1-byte variable, it works. But if you start with 1,
well, that makes sense because you're declaring 2 bytes of location, so that's fine, 16 bits, and then you declare it 1, so you still have that location, then you just have the lower part of it.
Okay.
It makes some sense, I should say. It doesn't make a lot of sense.
Okay, cool. That's all I had. I was just confused last night. So.
Yeah, no problem.
Thanks.
Brighton? Yeah. Wait, you don't want nap time?
I'm sorry, what? Ooh.
Is that better? could use a microphone too and be louder. The acoustics in this room are actually terrible because the walls are so reflective. If you're sitting here and talking, then you get like weird reflections back. All right, everybody ready for a quiz? Not like a real quiz, like just feedback quiz. Does this question make sense? Okay. You're allowed to Google this. Are you able to access all the questions at once?
No.
Oh, okay. Yes.
Never even heard of a nipple before today.
That's right. All right, everybody voted. Yay! We all got it. Nice work, everyone.
Maybe Google it. But I do wonder, what is the purpose of a nipple?
It just comes up here and there. If you had an 8-bit processor and you had a 4-bit operation, it's easier to say nibble than 4 bits. Just like it's easier to say byte than 8 bits.
Well, yeah, but half a body.
It's easier to say that to you. That's fine. All right. Okay, question 2. How many bits are in a byte? Okay. Nice. We all got that one right too. Way to go, everybody. Okay, last question. So a word is different in that it depends on the processor. Nibble and bytes, to my knowledge, are just standard computer jargon across everything.
Are we allowed to look this up, or?
Yeah, you're allowed to look it up. Might be a little harder to look up. Okay, I'll make it a little easier. It's the word in this case would be in the ALU or in data memory. I think the term program word might be used in the manual at some point, so that could make it more confusing.
Something about this is a lot, but
Two more people.
it's dying.
Everybody in? All right. Okay, yeah, this one, it's 16 bits. But in some processors, it is 8 bits, and some it's 32, and the instruction words are 24. So it's understandable why it might be a bit more confusing. But the word, and this is just in the data sheet and the programming reference manual, it's nice to know that the word is 16 bits. Okay. So I have another question. That is, um, so how many bits wide is program memory?
It's going to say 24 until we sign in for it.
Yeah. Yeah, it's the instructions are 24 bits wide. In some places, they call program memory 16 bits and have each program take 2 spaces. But instructions are 24 bits wide. Okay. So let's just say program memory is 24 bits. How about the ALU? 16? Okay, yeah. How about data memory? Yep, 16. So, okay, more quiz type things. How long does an instruction take in seconds? So that's, 1 over 16 megahertz. And that's if the CPU is at what frequency? Okay. So if the CPU is at 32 megahertz, that's basically how fast the clock is, right? The clock is going up and down and up and down and triggering everything. So that's at 32 megahertz. And then it takes 2 of them for each instruction, right? Okay. So then the instruction frequency is 16 megahertz. Because it's 2 clock pulses per instruction. So then the time it takes is 1 over 16 megahertz, which is 1 over 16 microseconds, which is 62 nanoseconds, 62.5 nanoseconds. That's pretty fast, 62 nanoseconds for an instruction. So how long do you think a function would take? Just a ballpark guess. If you wrote it in assembly versus if you wrote it in C. What's a guess for how long a function might take? If you just call the function, say in MATLAB, you know how you have you might have a function which does a bunch of stuff on an array. And you can see how long it takes. A lot of times in MATLAB it takes a long time, right? So in the microcontroller land, how long do you think a function might take? 10 milliseconds? 100 milliseconds? Why do you say that? Based off the lab, but that was like a long function, right? Because it had a bunch of loops. You wanted it to be as long as possible. Does that make sense? But say you just had a function where you're just adding 2 things together. I guess that should be more specific. So say, yeah, sorry. Say you just had a function where you're just doing an add operation. How long do you think that would take? Just one instruction? Yeah, that makes sense if it's just one instruction, but say you have to call a function and you have a couple different variables. Say you're adding 2 64-bit numbers. Why do you say that? You're thinking 10 instructions? So we covered like the stack. Each of these saving things, if you're going to use a stack, each of these saving things is like an instruction cycle. I think saving the program counter actually, I think the call takes 1 instruction cycle. So it does all of that in one, which is pretty nifty, which is... the call takes 2 program memory locations, but I believe it just takes 1 instruction cycle, but we should double check right now.
Yeah, I'm kind of looking at it right now. It says 2 number of cycles. It says 2 per call.
Okay. Well, that makes sense.
I'm looking at page 55. No, 226.
Okay, compare, skip, program flow. Oh, yeah, they do take 2 instruction cycles. So the call would take 2, which makes sense because you have to save the program counter and you have to move the stack pointer. So it makes sense that it would take at least 2, but it takes 2. Okay, so that's 2 just to call a function. And then if you're saving 4 things in the stack, that's 4 for push, and then you also probably would have 4 for pop, so that's 10 already before you even get into the function. And then once you get into the function, if you have to add 4 different things, that's 4. And any move operations that you would need to do could be like 4 more. So you're getting up to 18 instructions, maybe rounded off to 20. So this is a reasonably sized function, adding two 64-bit numbers, and we're looking at maybe 20 instruction cycles. So function on average might be 20 to 1,000 instruction cycles, maybe. Let's just say 10 to 1,000, which would be 600 to 60 microseconds, right? 600 nanoseconds to 60 microseconds, something in there. So let's just say a function call would be on the order of 10 microseconds. So it depends on the function. So like if you're doing something like processing a sound file, doing an operation on you're recording some sound coming in and you're doing an operation on it. This, what would your limitation be in terms of speed? So if what you're doing is just a delay, if you're doing some processing on the sound and putting it out and there's just a delay between input and output, I think the human ear, you'd have to figure out what the human ear is, and it's on the order of a millisecond. So you have to do all of your functions in a millisecond. And it seems like that might be a reasonable thing to do with this processor. So when you're selecting a processor, sometimes you have to do this kind of math to kind of think about what sorts of operations you'll be doing, how many instruction cycles they take, and how long that would take in terms of clock speed. Any questions? It's kind of like a little quiz section of the class. It is 2 cycles. Branch is, a relative branch is 1 cycle. But branch doesn't do anything with the program counter. You branch and then your SOL, if you need to come back, you just need to know where you came from. Our call actually still takes 2, but it only takes 1 word of program memory space. Okay. So I wanted to mention you can program a stack overflow called stack pointer lim, SP-lim register, and it will check to see if your stack has gone over the stack size, and if you do, then it generates a trap, which is kind of like an interrupt, which moves the value into the program counter, and you go to this vector in program memory space, and then you decide what to do from there. I have some stuff in interrupts, compare, multiply, divide. How many people want me to talk more versus getting out early for class? I can put some questions on these in this week's homework. Multiply, divide, and compare are pretty easy concepts. It's just I'd like to go over the syntax a little bit. Interrupts, I might have a real quick question on that. But otherwise, it's Friday. Might be nice to get out early. Yeah. Okay. Well, I kind of want to end now. All right, so I'll post the homework today and talk about, we'll have a lot of time to talk about interrupts because basically every single Every single peripheral will generate an interrupt vector, and we'll have lots of time to go over those. So, otherwise, see you Monday. And if you need more time in the homework, send me an email, please. I'll see if I can post that today, too. Yeah. Oh, shoot. Would people want to still do a...
I just requested Monday to Wednesday, so I have no time. I stress myself out
So I scheduled the one-on-one for like today at like 12:30.
Okay.
But seeing as how we're done early,
No, I'll be here.
yeah.
You don't, I mean, if you want to reschedule, that's fine.
I'm just saying, like, could we like just run through 15 minutes now, or
Uh,
if you don't want to, that's cool. I mean,
Can we do it at... Would that be more convenient for you? Yeah, we could.
yeah, because I mean, I have nothing until 12:30.
For... Oh, you have nothing till 12:30? Yeah, that's
Yeah.
fine.
All right.
So I'll be in 2-1-27 just as soon as this is all wrapped up.
Awesome. Thank you very much.
Yep.
Here you go. Here you go.
Thanks.
Oh, by the way, are these allowed? I don't plan to open it, but in the lab. But
In the lab? Sure. Just leave it away from the computers.
I can't afford it. I can't afford to do that. Imagine. Or better yet, just do what I always do.
Oh yeah. Yeah. No, I'm not that busy. Thank goodness. Homework. Were you at the homework over there?
Yeah, over there.
What's going on for the weekend, Mike?
Oh, I got kids. We got a birthday party to go to.
Oh,
Date night with the wife.
Oh,
Anniversary
Could I set up a one-on-one with you on Monday?
Oh yeah.
Yeah, sure. Like right after?
Whenever you're
Okay. So that's the 27th?
Any plans?
going
Sure. How about...
Sweet. That'll be awesome. We're in Wisconsin.
It's let me check. I don't know.
One.
They got
There,
rock
yeah.
climbing.
How about,
I know it's gonna be a lot of fun.
is it,
That's gonna be
how
unreal.
about 10:15?
Like
Yeah,
2
that'd
hours
be
away
great.
from the
That's fine?
Yeah.
Okay, great.
Good.
Thank you.
Yeah,
Enough.
thanks.
Not too far, so it's not like a terrible day. Can I ask you a quick question?
Yeah.
Just with the staff, I just want to overview it and make sure I'm taking it in.
Yeah, definitely.
Understanding is thorough enough on that. Just with Stack, we're using Stack in call function, and my understanding is the Stack is that's like a temporary workspace we're going to use if we want to return a value or do something to a variable, but we don't want to like kill everything in our code.
Yeah.
So we have our frame that's going to hold our local variables from our thing, right? In a
Yeah.
sense, we're going to copy what we need to into the stack to do manipulations that we want to do.
Yep.
When we do that manipulation, if we want to return a variable, we then have to take that variable and we have to change it up here. Is that right?
Or you could pass it back in one of the working registers.
Into any working register is fine.
hopefully not one that you're gonna pop out of the stack. Or,
That's my next question with the pop
Yeah.
and the push. So when we
Yeah.
push a working register into the stack saying we're going to use you.
yeah, we want to save you because the function will use you and destroy it. You know.
Yes.
So
So
you
we want to
wanna save
protect
it.
our
Yeah.
code.
Exactly.
When we pop it, we're popping back. Why do we pop back stuff that we don't even need to use? Is my question. Why would we pop back?
It might be integral for part of the function.
Okay.
So it might be an important part of whatever function this is doing. So when we call a function, we might want to use them for that function, but then restore them once we get back.
Gotcha. Restore them in their original sense, or
Just
once
whatever.
once you restore them, like if you got W0, W1, W2. My idea is this was say 1, 2, 3. Now when we're done doing our whole stack and all our operations, it's 4, 5, 6. Is that possible? Can these variables change within the stack, but they don't change up here?
You mean working registers?
Yeah.
4, 5, and 6.
Or no, the value within W1, W2, W.
Yeah, those might change. So they might be 4, 5, 6.
Yep.
So if you want to pass them back in those values,
What if I want the original values though? What if I only want W2, but I needed to change these two to get W2?
right? So you could increment and decrement the stack pointer then manually. You probably wouldn't use push and pop because push and pop just
Takes this value and puts
Yeah.
it back into here.
yeah. So what you could do is
Okay.
You could-
that makes sense.
you could
So
pop this
let's close.
value. You could pop this value to some garbage register because you don't care about what it is, but you don't want to overwrite what's in W2. So you could pop it into, for example, 6, 5, 4, and then maybe your function would pass values back in 0, 1, 2. So you would pop the values to decrement the stack pointer. You
Okay.
wouldn't necessarily pop them back in the same place.
Okay. That makes sense. And then frame is literally just our saving spot. Our
Yeah, it's
holding
like
spot.
you know how sometimes in the homeworks or labs you declare a variable up there,
Mhm.
and then it's got a memory location in the data memory.
Yeah.
So this is kind of like a more organized way of doing that, basically.
Gotcha. Okay. Cool. I appreciate it. I just wanted to make sure because a couple of us had different ideas, but I think I'm on the right page with how it's working in the flip of it.
Okay.
Just how it's processing too, and why I guess you use it.
Yeah.
Cool. All right. Thanks.
Yep.
You got plans for the weekend?
I think so.
That's all right.
Yeah.
Play it by ear. That's the best way, though.
I think I got a wedding to go to.
Oh boy. Party time.
Yeah.
So where's it at? Is it close by?
Yeah, it's in the Twin Cities.
Okay.
I don't know exactly where.
That'll be fun. Hopefully the open bar.
Yeah, it's not open bar.
Oh, bummer.
It's a Christian wedding,
So
so
there's no bar.
we might have to smuggle in our own. So
In the water bottle.
yeah, exactly.
Christian wedding. I don't know they-
It's
Well,
my
it's Christian, not like because Catholic weddings. Lord knows they bring the liquor.
yeah, I
You know what I mean? Like Christian weddings, I guess it must be a little more.
No, it's my girlfriend's friend, and I think she's sort of like in the Lutheran kind of, or like
It's more strict.
yeah, more strict for some reason.
Huh.
But yeah, that's a good point because Catholic weddings you get lots of wine and booze and beer. And
Oh yeah. I grew up Catholic, and boy oh boy, that
Okay.
was like the coming out. You know,
That's like the one time
during service, they are just, mellow and as patient. The moment that you come out, I think that's why they give the Eucharist way at the end, because then you get the blood, the wine,
Yeah.
that gets everybody started.